So just how many protons and neutrons are there in something really big like the Sun? Now, in order to estimate the total number of very, very small things in something really big, we need to know two bits of information. We need to know the average mass of these protons and neutrons, and we also need to know the total mass of the Sun. Now, the total mass of the Sun is equal to 199000000000 kilograms. So that is a massively large number, and it actually takes just a long time to even write it down. Now, when it comes to the mass of the protons and neutrons, I'm going to be using something called the atomic mass unit. Now, that's just the average mass of nucleons that you have inside all atoms, really. It's just an average number, but again, that's going to be good enough for the estimate. So the average mass of a proton or a neutron is equal to 0.00000000000000166 kilograms. Okay, so that is the atomic mass unit, something incredibly small. So how can we actually work out the total number of the small things and the big things? We just take the large number and divide it by the small number. Now, of course, when you start putting this into your calculator, it's really difficult to actually keep track of the total number of zeros that you've entered. And there must be a better way, which is why we have standard form. Now, this standard format means that we can write really, really big numbers and really small numbers, and also actually look at the significance of the figures that we've got. So what we can do with the top one is we could write this as 1.99, and the first number is always going to be between 1 and 10. And then we're going to say this is times 10 to the something. Now, we've got to think really about how far we'd have to move the decimal point back to make it sort of go between the 1 and the 9. So if we're to move it 3, 6, 9, 12, 15, 18, 21, 24, 27, 28, 29, 30 places along, we could also write this as 1.99 times 10 to the 30 kilograms. So that is the mass of the Sun. If we did the same with the mass of the protons and neutrons, again, the first number would be 1.661 times 10 to the something. But now we've got to think about how far, very simply, how far we move that decimal point, in this case to the right, until it ends up between that point over there. And here, this is actually times 10 to the minus 27 kilograms. So these numbers now are the same numbers. They're just written in a much simpler way to understand. And also, as we're going to come on to look at, if we've got 3 digits here, that shows that that number is actually written to 3 significant figures, and this one's written to 4 significant figures in this case. So then, when it comes to the calculation, it's relatively straightforward. We just write 1.99 times 10 to the 30 divided by 1.661 times 10 to the minus 27. And that means you can then easily work that out on the calculator, which gives a number of 1.1980735. But of course, that's not the best way to display it. We've actually got 3 significant figures there. So we could say this is equal to 1.20 times 10 to the 57. So that is the overall answer for the question. There are 1.20 times 10 to the 57, approximately, protons and neutrons in the Sun. So standard form is used a lot more in A-level physics, especially compared to GCSE physics. We have really large numbers, we have really small numbers coming up all the time in our calculations, and it also means that our final calculated value, as well as knowing the size of that number, we can often show the number of significant figures we've actually calculated that number to. And this video is just one of many that I've got as part of my maths mini course, which is ideal for anybody starting A-level physics. I've got lots of videos that cover all of the main maths topics, as well as plenty of worked examples to help you see how this can be used in an A-level physics context.